Ohm's Law, Lesson 1A. Ohm's Law says that the resistance doesn't depend on the voltage or the current, which is kind of a strange thing, because if you look at the actual formula, you see that delta V equals IR, and you would think that the resistance depends on those two things, when in fact if you increase the current, the voltage changes, or if you decrease or increase the voltage, the current changes. The resistance doesn't change. The resistance simply depends on the material of the resistor and the geometry of the resistor. Additionally, the variables are delta V, which is voltage or potential difference. And so you can kind of think about voltage as like a potential energy. If you lift it up, it has a high potential, and then if you let like a book go, it goes to a lower potential. So things want to float from a high potential to a low potential. So there's a change in the voltage, just like there's a change in the height or change in the potential energy. The battery supplies a high voltage, and then it goes around the circuit and comes back with a zero voltage at the end of the circuit. Current is measured in amps, named after ampere. The symbol is I and the variable is A. Resistance is measured in ohms, and the Greek symbol omega is that kind of goofy looking upside down U. Now, how do you decrease the resistance of a resistor? So would you use a larger cross-section or a smaller cross-section, do you think? Well, if you think about it this way, if you were to have 50 people outside a door and try and get through the doorway, would you want a large door or a small door to decrease the resistance? Of course, you want a larger door, so the answer to this is larger. How about the resistivity? Well, that's simply the actual material that it's made out of, and you'd want a low resistivity to have a decreased resistance. And how about the length of the wire? And so the length of the wire affects things in this way. Of course, the more wire there is, the more atoms that the electrons are going to encounter, and the more resistance that they're going to have. So if you want to decrease the resistance, you have a shorter length of wire. So this is kind of all summarized in this slide here, but if you kind of look at it, the length here, as that goes up, the resistance is going to go up. If you look at the area, that's an inverse proportion with resistance. As the area goes up, the resistance goes down. And resistivity, high resistivity means high resistance. And the units for resistivity are ohm meters. And so if you look at the dimensional analysis, if you have ohm meter times length meters and divide that by the area in meters squared, the meters squared cancel and you get resistance in ohms. So it's kind of a strange unit. It's a multiplied unit. We don't see that a lot in physics, but that's just the way it is. Superconductors are great. They may be part of the future. They have very low resistance, which that would be good, because things with electricity require a lot of heat, and there's frictional losses there, and so superconductors have very little frictional losses, And the idea is to get something very, very cold, but you usually have to get down to about 1,000 or 100 Kelvin, which is like negative 273 or whatever it is, Celsius, which is pretty darn cold, and that creates, it takes as much energy to cool things and to keep the system cooled as it does the energy savings that you get out. So currently right now there's a lot of research going into superconductors, but they're not necessarily a viable solution.